10 minutes, I think. 10 minutes or 5 for him. Well, thank you very much, Chairman. Thank you very much. Thank you, Jesus, for inviting me for preparing this presentation, also paper, which is co-authored also with Professor Montserrat Lopez, Nicola Tosic, and Pedro Serna. Good. So, okay, like this. Yeah. So this is the paper. Yeah, Andrea. Sorry, Andrea. The title was incorrect. She's Andrea. Yeah. So what I'm presenting here is the paper. Yeah, with this index. As I have 10 minutes, so I will be I'm not going to the details. Yeah. So I'll go to the important things. So Fire Force concrete is a material with which we are already familiar with. It has been used so far for pavements, repairs of structures, also supporting ground support and with shotcrete, and also precast concrete linings, some flat slabs, eliminating even the reinforcement, architectural applications, and some precast concrete elements like sewage pipes, electric cabins, even here in Madrid for the 3D printing concrete footbridge. Yeah. But well, some even of these structures were even designed without any recommendations of islands, yeah, 15, 20 years ago. But after the acceptance of these materials in structural use, some guidelines appeared. The first was the German, then the relevant recommendations, then the Italian FIB model code, even in Spain. Nowadays there are guidelines for design and fire force concrete in New Zealand, in United States, Canada, a lot of countries. Yeah, but now the Annex L allows us to have an harmonized European regulations for fire force concrete that nowadays covers only the steel fire force concrete and is informative. Yeah. So regarding safety format, also the design also follows the partial safety format approach. Yeah, and the safety coefficients that were accepted for the concrete, yeah, for compressive and the tensile pre-crack and residual tensile strength is 1.5, 1.20 in case of accidental loads, and 1 for serviceability limited state. Yeah, and I want to emphasize, to highlight that even with the high variability that can have the post-cracking strength of fire force concrete, which can vary between 10 up to 30%, these coefficients are sufficient for guaranteeing the reliability index of 3.8 that has been accepted. Yeah, but in any case, there are some elements, yeah, that are repetitive, like the precast concrete elements, or other elements that in some cases it's even necessary or recommendable if we want to optimize the design to calibrate the safety factors. And for this, we can use the Annex F of the Eurocode. Yeah. So in terms of material, the use of steel fire force concrete or the steel fibers initially does not modify significantly the mechanical properties of the material. Yeah, the compression, tensile, pre-crack strength, the modulus, the shrinkage, and the grip in compression. In case that the permanent loads are high and also the crack width in service is expected to be high, then the grip in tension can be a determining parameter. And in this case, the Annex L proposal suggests to make a test, yeah, to calibrate or to characterize the grip behavior in tension. So the material is classified in strength classes based on the characteristic value of FR1. FR1 is the flexural residual strength for a crack mouth opening displacement of the beam test of 0.5, yeah, which is related with the service limit state. And then the ductility ratio. Ductility ratio is the ratio between the FR3, which is the characteristic value of the flexural residual strength for a crack mouth opening displacement of 2.5 divided by the strength class. Yeah. So with these two parameters, we can classify the steel fire force concrete in tension, in flexural residual strength. Yeah. In terms of ductility, we have A, B, C, D, E classifications. Good. And in terms also of design, yeah, the ratio between the characteristic value of FR1 and the tensile strength, the characteristic value, yeah, the percentile 5%, should be superior than 0.5 to guarantee ductility of the material, especially if we are going to substitute or eliminate part of the longitudinal reinforcement. And the design values of the tensile design strength, residual again, yeah, in case of service limited state, is governed by the FR1 value characteristic. And we have also to consider the orientation and the size factors, yeah, both for the serviceability and for ultimate limited state. Yeah, the difference here is this factor, and that for the ultimate limited state, we relate the resistance to the 2.5 millimeter crack mouth opening displacement value for FR3. Yeah? As per the orientation factor is 0.5, unless it's verified by testing. In any case, never superior to 1.7. And in case of consistency classes, yeah, 215, it's 1. It's suggested to be 1. The size effect factor, yeah, that is a corrective factor for taking into account that the variability of the residual strength reduces with the cracked area, is assumed, or this formulation can be used where the area is the ACT is the area of the cracked region, and never superior to 1.5, because if we take values superior to 1.5, we can clash with the statistics, and we can end up with values of FRK superior to the average, right? So for nonlinear analysis, this is the constitutive equation suggested. Is a trilinear model, yeah, with the pre-crack constitutive relationship linear for before the cracking, and then after the cracking we activate the post-cracking resistance of the steel fireforce concrete, and we characterize this curve with these two values, with the effective value of FT1 and FT3. For compression, I leave the floor then for my colleague. And then in terms of durability, yeah, we have to say here that the use of steel fibers do not lead to reduction of the durability response of the concrete. Yeah, this durability is governed by the longitudinal and transversal steel reinforcement. But in any case, the Annex L asks for a minimum cover of 20 millimeters to guarantee that there is no accumulation of fibers in the bottom or in the borders of the section, and also for the sake of safety, proposes that in ultimate limited state not to take into account in the contribution in tensile residual strength if in these exposure classes, yeah, in case that no cracking is expected in ultimate limited state, in service limited state, sorry, in ultimate limited state, we can consider only 10 millimeters of concrete cover, and in case that cracking is expected or accepted in service limited state, we can use, or we can accommodate these this concrete cover with a reduction factor, which depends on the calculated and the limit value of the crack width. For ultimate limited state, there are two constitutive equations proposed. One, rigid plastic, yeah, which is defined by the design value of FR3 divided by 3. This is tensile residual strength. Or for more accuracy, we can go to a bilinear constitutive relationship. I must say here that with the database that we have, yeah, and this is gathered in the background document, that the accuracy using this constitutive model, compare it with the flexural tensile test of beams, the average error is it's 1, and the coefficient of variation of this error is 8%. So very reliable models, although very simple. As for shear and punching, yeah, the use of steel fibers improves, yeah, the control of the crack width of the shear crack, and also the aggregate interlock. This has been seen in test, and the higher is the FR3 value, the higher is the contribution of the fireforce concrete in the shear strength. The model, which is accepted in the Annex L for taking into account the contribution of the steel fireforce concrete, it's also based on the critical shear crack theory, yeah, and this is formulation. I'm not going to enter into. Sorry, I went to, yeah, I don't shear first and punching. I think it's, sorry, because I just jumped a slide. So this is the same formulation accepted for the shear of reinforced concrete, and we can take into account the contribution of fibers adding to the other contribution of the concrete or the stirrups in case that we put stirrups. Yeah, and with this factor here for punching.
10 minutes.
Okay, sorry. Yeah, just 1 minute. And also for punching, the very same. For torsion, yeah, we have two mechanisms, and these two mechanisms, yeah, also we can consider the contribution of the fire force concrete. And as for fatigue, just to say that the contribution of fibers in fatigue, in compression, and tension was not considered in design Excel because there were clashing results, yeah, in terms of fatigue. Yeah. Good. As for cracking, is the same, also the same formulation, except that for the crack spacing, also the effect of fibers can be considered, and also the effect of fibers can be considered when calculating the strain or the strain of the steel, longitudinal steel. Yeah. And for finishing, yeah, for likely reinforced concrete structures, those structures that are designed with amount below the minimum reinforcement, the Annex L allows this type of structures, but recommends only for statical indeterminate structures. Yeah, and in some cases, yeah, for some elements, proposes a minimum resistant class of the concrete. Yeah, for the utility. Yeah, as for conclusions, just to say that this Annex L is the first harmonized guideline that covers the use and design of steel fire force concrete, and that even this guideline allows for the partial or total replacement of longitudinal and transversal reinforcement. That's all. Thank you for your attention.
Okay, good afternoon. So my presentation is complementary to the one of Alberto de la Fuente, and I'm going to talk about the compressive behavior of steel fiber reinforced concrete in the new Eurocode in Annex L. So just the compressive behavior. And my co-workers are Ángel de la Rosa, Lisa Poveda, Ricardo Zanon, Marcus Schaffer, and Sebastian Wolf. Three of them are present in this meeting. This is the content, introduction, the behavior in compression, an application example, and some conclusions. Albert has been talking about mostly about the behavior in tension. Here you see a picture in which you see the fibers that are showing the crack. So obviously they provide a lot of toughness and a lot of energy consumption in tension, but very little attention is put into the behavior in compression. In this case, I'm putting an image of a DIC. It is a DIC image of a composite structure in which you see that there is a big compression field in the top of the beam, which may have some impact on the structural behavior. So now I'm going to try to explain with an example why we believe that considering compression in fiber reinforced concrete is important. So in this case, we are going to consider kind of a problem in which we are going to see what are the provisions that the Eurocode 2 in the core of the Eurocode gives for this particular concrete, which has compressive strength of 54 megapascals. This is the elastic modulus, 33 gigapascals. The fiber ratio is 0.6%, and the residual flexural strength, one characteristic, as Alberto explained, is 4.1. So if we go to the core, I mean to the main Eurocode, then we are getting this curve. So this is the curve that we are getting, which is fine. So we have all the elements. But if later on we go to the lab and then we make this concrete and we produce it and then we test it, then what we get is this. So there you see a lot of curves, all of them are real, and all of them correspond to this concrete. And then it is clear to me that there is kind of, this like we are not taking advantage of all the behavior that this material has. Because you see, yeah, there is a consistent softening, but we have a lot of energy consumption, and we have strains which are very long. So now, if we apply the model, the new model that it is inside an Excel, what we get is this orange curve. This orange curve, later on, I'm going to say what is the equation, what is the formula, but it is clear that it is a bit more appropriate to, according to the experimental results. And I have to say that this orange curve is not a fitting. So it is not a fitting. So it is just what we get if we apply the formula in the model an Excel with these parameters that we are having there. So of course the difference in terms of energy per unit volume or toughness that you see there, which is this gray area, and that one are a lot. I mean, it is more than 2 times or several times the energy per unit volume, the toughness that we can get. Okay, so what is this equation? Actually, it is a very simple thing because we use the formula, the same formula, the same equation of Sargin, which is that one in this corner. So that one, it is exactly the same one as for plain concrete, but we modified slightly the critical strain for the peak. So here you see that there is a parenthesis which is multiplying. It depends on the residual flexural strength for an opening of 0.5 millimeters, the characteristic value. And then a particular thing that has to be carefully observed is that that equation here has a parameter K, and this parameter K has one value in the ramp-up curve that depends on the elastic modulus, and then another one in the softening part, which depends on, again, on this residual flexural strength. So this very simple equation is what we have seen in this orange curve. So what, we also made a contribution for the ultimate limit state. So in this case, you know that we use the parabol rectangle curve, which is mostly defined by these 2 parameters plus the strength parameter, of course, the ultimate strain, and also the strain for the peak. These parameters for plain concrete are 0.2% and 0.35%. And we kind of mimicking what we have in the core of EC2, we were given constant parameters for any flexural class, which are 0.25% and 0.6%. This is for any class. However, I have to say that these parameters, of course, they are related to the flexural class or to the strength classes, as Albert was saying. So in the paper later on, if you read the paper in detail, you can see what is the relation, and then you can see how you can have, let's say, strains which are way bigger than 0.6%. So what is the impact of this in a structure? So here we selected an example. This example is a composite structure, which you see there is steel profile and this concrete flange. And then here in the x-axis, we have the curvature of the cross section, and in the bending moment in the y-axis. And then here you see that, let's say, for the plain concrete in the compressive head of the composite beam, we are reaching there. We are getting 91.8% of the plastic moment. And then we have a rotation, which is approximately, they are 12, 1 over meter, or meter to -1. But if we use fibers, then we can double the rotation capacity. We double the rotation capacity. And of course, we are also doubling the energy consumption capacity of this section. We believe that this is an important thing, at least for composite structures. Maybe if you don't have a structural steel, the benefits are not that big. But in any case, in this particular example, you see that it is important to use fibers. So my conclusions are that the annex of the new Eurocode 2 accounts for the additional ductility due to fibers. Also, that compressive and flexural classes are coupled, even though I didn't explain this in detail, but it is in the paper. The ultimate compressive strain in the ultimate limit state goes up to 0.6%, which is a lot, and it can be more than that. And these new criteria are advantageous for composite structures and for any other structure. So this is the paper that you can read. You can read it now printed, you can download it, right? And I have to say that we also published another paper in a journal, a German journal called Stahlbau, in which we explain this in maybe more detail, at least the structural part. And then we have this subtitle, which is an outlook in a new generation of composite structures. We believe that this can be a leap forward when steel fiber reinforced concrete is combined with structural steel. And that's it. Thank you very much for your attention.